somebody new on the way back. And he's getting me a cup of coffee. So some you know will be joining us in class apparently.
The second year.
Okay, hi, welcome back. Thank you all so much for filling out that survey and for the feedback. I really appreciate it. I'm going to try to change. But I'm an old dude. But seriously, no, I take it really seriously. Every time I get feedback at this kind of when I get feedback at the end of the year, I do try to change how I do things. I'm still trying to process exactly what the key signal to take away from the feedback is. You know, I've had this weird thing where, like, I sent out the survey, and by last night when I went to bed, it was really good. It was a curve like this, where, like, this was too fast, and this was too slow, and, like, it was mostly, like, most people were like, it's fine, and then some people were like, it's fast, but I'm keeping up. And then there was a long tail. And then I woke up this morning, and it was like, because, like, some slow things happened at the end, you know what I mean? And so like, obviously, that makes me want to say, I want to slow down a little. At the very least, slow down my mouth. And possibly resist the urge to go on as many tangents, because we can't actually slow down the pace in which I'm presenting the concepts, or we won't get through all of them. So what I would encourage you to do is, like, keep me honest. If I'm speaking too fast, or certainly if I said something you didn't understand, stop me, you know, make me say it again, and little by little I'll learn, you know, what to say slowly with gravitas and emphasis, and what I can sort of just travel off with my back to you. And then I would encourage those of you who sort of filled in this thing late, I hope that you're taking advantage of office hours. I hope you consider doing so, because we've had a bunch of really quite productive and well-attended office hours, in which a lot of the stuff we've been discussing in lecture has gotten reinforced. And so the perfect thing to do if you feel like the pace is a tiny bit too fast is to attend office hours. That's not me advocating responsibility for teaching at great pace. So I hear you. Okay, thanks. And so, on a similar note, a couple of you expressed this thing on Piazza last night that, like, oh, I was keeping up, and then yesterday everything went to hell. And I'm trying to understand where things went off the rails on Wednesday. Did it have to do with the bit where I was drawing those stacks? What was the confusing thing about Wednesday's lecture, if anything? Was anybody confused by Wednesday's lecture? Was it me jumping back? Yeah, please.
It was the stack part.
It was the stack part, so let's spend some time on that today. Okay. Well, let me explain what I meant by that, because I think it's a visual metaphor that I'm going to try to use a bunch more times in this class, and I think that probably I went too fast. And so we're going to be talking a little bit today about, like, what our sort of abstract API looks like when we start implementing replication protocols. And obviously, this is going to be sort of what you do in your homework. It's going to be a very important subject for this class. Thank you so much. Of course. Let's go slow. And let's talk about how you build an API on top of another API, calling the functions below and exposing functions above, right? So let me just draw this sort of a little bit more explicitly as a puzzle piece. We're imagining that the network itself has a couple primitives that it provides us with. And by primitives, I mean operations that can't really be broken down into the operations they're composed out of, right? So imagine that this is the network, or this is basically like, this is the network in our operating system. This is the sort of bottom of our stack, right? Corresponding to this world that we live in, of process timelines that proceed downwards and absorb and emit messages, right? So at the bottom, you might call this send, right? And send, let's just think about it as a function that takes one argument and a completely uninterpreted payload m that is the message, right? So I'm a process timeline. What moves can I do? Well, I can do local computation, but that's sort of nobody else's business. But then if I want to interact with other people, I can call send, right? And that makes a message get sent out to the network with really, really few guarantees about when that message is going to be received, whether it's going to get received, all that good stuff, right? And then we can imagine that this API also provides an event that can be triggered when a message is received. And that's just called, like, receive, right? And receive returns the message payload. Right? So I send M, then I can say M equals receive. Okay? That's the bottom of our stack. And then what I was trying to illustrate the other day is when we implement, let's say, reliable delivery exposes an API, which is implemented on top of this existing API. Because what does reliable delivery do? Well, sometimes it sends messages, and sometimes it decides, actually there's one more thing, right? There's one more thing. And that's like, let's see, make it a square. That's deliver. Remember, I made a distinction between receive is something that happens to you, and deliver is something that you decide to do. Oh wait, yeah, there wouldn't even be deliver in this picture, would there? All this lower API does is send and receive. Then we said, okay, well, let's talk about reliable delivery. Well, what does reliable delivery do? At some level, it, put that too high, which is the RD. It provides an input of the same shape. Let's just call it rsend. And it takes a message out. It's just like send, except it makes this additional guarantee that the send will be reliable. And reliable delivery says when things are delivered. Right? So if somebody wants to send a message, they kind of have two choices. They could just send it and pray by calling send, or they could reliably send it by calling rsend. And rsend's implementation calls send, but maybe it calls send a bunch of times, right? It calls send as many times as it needs to. And now there's acknowledgments, but that's not part of the API, right? Acknowledgments are just sort of internal details. Okay.
Question?
Yeah.
So when you're calling reliable delivery, you're going straight to that protocol, and the protocol would use the bottom of the stack?
Yeah, the idea would be my client calls rsend with her message. And rsend, we happen to know, is going to call send. But not just one time, right? It's going to set up a timer, set up a buffer, call send periodically, and keep doing so until it receives an acknowledgement.
Okay.
But then ultimately deliver something. And the delivery just kind of percolates up the stack. And then finally, somebody might say, oh, okay, well, reliable delivery is great, but what I really want is ordered and reliable delivery. I say, okay, well, then I could create something that looks like this. Same exact interface, except we're going to call it FIFO reliable send, or something like that. And we similarly have, no, I can't draw it, but there's a deliver thing, right? And now, what does FIFO do? Now, we know FIFO does this cunning thing, right? Which is that when you say that FIFO send a message, it says to rsend the message concatenate the counter number, right? And it delays delivery of a message until the message has the appropriate counter number, right? So now a programmer who wants to send a message has a variety of choices about where in the stack to do it. Do I want to send and pray? Do I want a reliable send with no particular ordering guarantees? Or do I want an ordered send that is reliable? And certainly we could imagine reversing these on the stack, or taking reliable delivery out of the stack and saying, I want FIFO, but I don't care about reliable. What is these things are orthogonal enough, and the interfaces look similar enough, that we can stack them in a way that it's sort of transparent from the point of view of the caller which of these they're doing, but they're enjoying different guarantees. Less confusing or more confusing than before? Less confusing. What is still confusing, if anything, about it besides the weird puzzle pieces that I don't know how to draw? Yeah.
I mean, are you familiar with the sequence diagrams? It looks sort of like the line port diagrams, but they're like function call sequences, and you have the arrow.
Sure.
That might be how I've seen this written before.
Yeah, so I'm not good enough at them that I would use them to do that. But in some sense, the point is that it's very often the case that a particular API is going to be a composition of function calls, right? That like reliably sending something is basically just saying fr send, rsend, right? Send event, right? You can do kind of functional composition. Right? Okay, questions? Yeah.
So in the second layer, so you said the client calls rsend with his or her message.
Or like the client out here we call like fr send, let's say, at the top of the stack.
So in that case, is that including, okay, when I get the acknowledgement, after, however many number of resends until I get the acknowledgement, that gives me reliable delivery, but then the order is with the message plus a counter?
Yeah.
Okay, that's it.
Exactly. Remember, because we study these separately, and I wanted to study them separately because in some sense they have nothing to do with each other. And now what I'm trying to show you is they do have something to do with each other because you might want to use them in concert, right? So what happened in FIFO? Well, what was the thing? We had a sequence number per sender and receiver. Right? So we had a pair of integers for every communicating pair. Append the numbers to the messages. Deliver a message when what? When it is next in quotes, right? Like when my counter has the same value as the timestamp on the message, that's when I deliver, right? So that's like, what is that? That is FIFO. It is an algorithm that ensures FIFO delivery. We looked at several. This is kind of the preferred one, the one that TCP does. Reliable delivery. How does that work? Well, buffer and periodically resend messages until they are acknowledged, right? That was an implementation that we studied of reliable delivery. Now, I don't talk about any of this crap in here because it doesn't matter, because from the level of an API, there's sending, there's delivering, there's receiving, that's it. And since these things all have the same API, they can be mixed and matched and combined in a variety of ways. Right? So this is to emphasize how they're completely orthogonal, and this is to emphasize how, because they're completely orthogonal, they can be combined in an unconstrained way. And so they have nothing to do with each other except the fact that they're all good things that you might want to mush together. Yeah? Okay.
Right.
Good.
So I have. What's the API again?
What's the
You
API?
keep saying
API.
API.
API, good.
It's
What is an
application
API? It's an
programming
application programming interface, right?
Okay.
What is the API around delivery protocols? You have sends of a message. You can receive a message. And you can deliver the message, right? In some sense, those are the three operations. And that's why when I asked you to break into groups and devise protocols, we said, well, what is a protocol? Well, a protocol is, at the bare minimum, a delivery protocol, I should say. At the bare minimum is going to provide answers to those questions. What's your internal state? What do you do when you send a message? What do you do when you receive a message? And under what conditions is it safe to deliver a message? Right? If you can answer those four questions, you have a delivery protocol. Yeah?
So very abstractly, an API is like a postman kind of, takes a message, delivers it to someone else, or it's like an intermediate step between the client and the...
I would say that these puzzle pieces, which are APIs, are like postmen. But API is much more general than that, right? An API could just be how you interact with your file system or something. Like API doesn't have to be distributed or having to do with message sending or communication at all. But I would say that these APIs are like, what kind of postman do you want? Do you want a forgetful postman? Do you want a scrambled postman? Do you want an orderly postman? Yeah, sure. Any more questions on that? So let's real quickly, thank you for helping me clarify that. Let's real quickly review reliable broadcast. So I want to make sure that everybody knows it, and it went fast on Monday, or Wednesday rather. So can somebody, I'm not going to draw it right on the board again, but can somebody give me the definition in terms of phrases and implication? What is reliable broadcast? Yeah.
If the correct process delivers a process or a message M, then all of the processes deliver a message M.
Excellent. And correct in that context meaning
That
that
it doesn't crash.
it hasn't crashed.
In that snapshot, it hasn't crashed.
Oh, and that reminds me, I promised to show you how we generalized to the omission model, and I never did. Okay, so that's reliable broadcast. And we studied a protocol that gets us there and no further. Anybody remember what it was? Before delivering a... Yeah, sorry.
I
was like if A sends it to B, B also sends it to C?
Yeah, so like before delivering a message M, every process first broadcasts M to every other process, if they haven't done so already. And you need to say that last part so that you don't do it forever. However, I don't care if you do it forever. All we're trying to do is solve reliable broadcasts, right? And so a broadcast protocol that just sprayed the area is fine. I never said it had to terminate, right? But in practice, you say, if you haven't done so already. So, but let me start again. Remember, Alice wakes up and says, Bob smells. And in this case, the problem isn't that we're worried about Carol seeing the response before the message. Alice is worried that Carol won't see the insult at all. Alice was working on this zing for a long time. She wants to make sure that even if she literally dies in the middle of saying it, Carol will still get it, right? So what that means is Bob, before delivering the message, is going to multicast the message, right? And then deliver it. And what that means, I'm going to try to do this with colored chalk as per your request. Except somebody stole my colored chalk. Nope. And then she, red in here? No, thank you. She dies, and she's not actually able to send the second half of the atomic thing. But Bob, before delivering it, sends it, and then he delivers. Okay? It's easy to convince ourselves that if Bob dies before he gets the message, no correct process ever delivered the message. If Bob dies halfway into sending out the message, no correct process ever delivered the message. So we're vastly correct, right? So we have a completely correct protocol.
I have one question. So
Yeah.
so B sends and then delivers. What if the message is lost? Does
Remember,
it still?
we're in the crash model, so message losses don't happen.
Okay.
Right? So the only thing that can happen is the process can crash. We don't have to be worried about receiving processes crashing, because reliable broadcast does not dictate the behavior of crash processes, only of correct processes. So the only thing we're worried about is a non-atomic send, getting a message to some recipients and not others. And we know that in the event that that was to happen, any correct process will finish the job of dissemination. Now this theme of finishing the work that some other process began is a really important thing in distributed systems. It's a form of recovery. We're going to look at it in the context of read repair in core and replicated database systems, and we're going to look at it in the context of consensus systems like Paxos. It's often going to be the case that there's some compound piece of work, some non-atomic piece of work that a distributed system wants to get done, and because processes can crash, compound work can get partly done, right? And work that's partly done needs to be backed out or finished. Right? So in this case, this broadcast protocol works by everybody who's participating in broadcast is offering to finish the work of a process that crashed partway through. Make sense? Cool. Now, let's imagine for a minute, though, that process is crashing. Let's not imagine. Let's go into the reality that I promised we live in this class, the omission model, right? So processes can fail by crashing, but that's not the only thing that can go wrong. Messages can be lost, which means even if A doesn't crash, some shit like this can happen. Bummer. Right? Or, but that's fine, right? Because B is going to relay the message before delivering it. But the thing is, right? Now I have this situation in which I have a correct process, B, that delivered a message, and I have a correct process, C, that didn't. So we're going to have to upgrade or level up our reliable delivery protocol to make it correct in the omission. I think this leveling up is fairly clean, actually. Anybody have any thoughts about how we could do it? Yeah?
Just throw reliable delivery.
Yeah, just rub some of that reliable delivery on it. Right? So for example, that would be a stack that looked like, whatever, I don't know, bottom. all are just sends and receives and we can snap them together. Because now we can take something that we understood that worked. Remember, in the crash model, we could just snap this on B. Over in the omission model, let's put reliable delivery in there. Now I know that point to point, everybody who tries to send something to another server will eventually get there if at least one message is allowed to slip through. And I know when it happens, so I know when I can deliver. I don't think there's that much more to say about that. Right? So we know the way you solve omissions happening between two endpoints is a well-understood protocol called reliable delivery that we've studied. The way you solve the problem of unicast communication being non-atomic and potentially interruptible by process crashes is a different protocol called reliable broadcast, which resembles reliable delivery, at least. Why do I say that? What do they have in common? Well, here's one thing that they don't have in common. Reliable delivery uses acknowledgements, and reliable broadcast doesn't. Right? But they have some things in common, such as
Reliable.
Keep sending.
raise your hand because I can't hear the mobile. What's everything? Yeah. Yeah, I mean, yeah, and a little bit more specifically than that, like they both try doing something as many times as they have to. Right? Oh, it didn't work. I'll try again. It didn't work. I'll try again. So absolutely, they both use redundancy to overcome loss. Right? Yes.
What do you mean by RD and reliable delivery and reliable broadcast are orthogonal?
I mean that, you know, neither of them make reference to the same internal state, right? So I could mix and match them with other protocols. And so there's no dependencies or constraints between them. They solve different problems, but they can be combined to solve the third problem, right? That we saw here.
Thank you.
Thanks, everybody. With me? Excellent. A lot of progress. That was cool. So, and now there's a big transition to a big subject in this class. We're going to spend a number of weeks on it. A subject that we already introduced you to, which is replication. I made this big cosmic point at the end of class on Wednesday that I like to think of like logical redundancy as this kind of umbrella that all these techniques fall under. That if you squint your eyes, the distinction maybe between retry-based techniques like reliable broadcast and reliable delivery and replication-based techniques like primary backup replication, which we're going to introduce today, are kind of the same thing. But of course, if you unsquint your eyes, you see that they're actually pretty different. And they tend to address a different class of problems. In particular, the delivery protocols try to work around the loss of messages by making multiple copies of messages. Whereas as a general rule, replication protocols are going to try to address the loss of entire computers, the loss of nodes, by duplicating the state of those computers and keeping them in state. Okay, so I made this point that in some sense, if you say fault tolerance is redundancy, right? Well, the way I would argue that is that retry is redundancy in the dimension of time, right? Whereas replication is redundancy in the dimension of space. And these dimensions aren't the same, right? In particular, this is cheaper, right? In some sense, like, it's cheap and easy to try to do something again if it fails the first time. And in fact, we can imagine doing something an infinite number of times or an unbounded number of times if it keeps failing. You imagine there's a basket, you got a basketball, it's just you on the court. You're just going to keep throwing the basketball until it gets hit, right? You're going to keep retrying. It's not like it costs you an incredible amount to do all those retries. No, we can imagine scenarios in which we have limited bandwidth and you wouldn't want to retry indefinitely. You're kind of throwing bad after good. You want to retry some number of times and then give up. But at some level, these are really cheap versions of redundancy. And it's redundancy that we can kind of choose at the last minute. We don't need to commit ahead of time necessarily to how many retries we're going to do. Whereas, if we have to get purchase orders and buy computers, and we have to power up those computers and spend a bunch of time getting the data on them, there's some real cost that we have to pay up front to redundancy in space, right? It's not just like it'd be like, oh, okay, well, that computer crashed, I'll just make another one. It's like, too late, buddy. The data's already gone. You had to think of that before the crash, as opposed to like this scenario where it's like, oh, message was lost, I'll just send another one. Doesn't cost me nothing to make a copy of a message. It costs me a hell of a lot to make a copy of a server with a whole bunch of state on it, right? Make sense? So it's going to turn out that these protocols are significantly more nuanced and significantly more complicated than the redundancy sort of techniques and recipes that we've looked at so far in the class. Before we get into the actual protocols, I think they're so awesome and so fun to teach. Let's take a minute and go slow, especially given the confusion from Wednesday around APIs, to talk about the model. Like, what kinds of operations are we replicating in replicating systems? Well, in this class, to make things pretty simple, we're always going to be looking at replication of data, right, as opposed to replication of computation or something like that. And I guess maybe the thing, I've never done this lecture this way before, so bear with me. Maybe the thing that makes most sense to talk about is to talk about like a single site version of it, because after all, that's what you're building in your homework. The way I'm going to model these systems, let's just imagine a single replica implementing a data store. When we start thinking about a data store, maybe it stops making sense to just be thinking about this world in which there's these sort of uninterpreted messages flying around, and all we care is that they have some payload down. All of a sudden, now it starts making sense to differentiate between the different types of operations we might want to do on a data store. What do you think are the types of operations you might want to do on a data store? Reading, writing, maybe that's it. Maybe deleting, maybe updating, something like that. I think the easiest way to model all this stuff, the most intuitive model, and one that I think generalizes to the types of data stores we see in practice, where what we're actually modeling is rows and tables, or we're modeling the mapping of values to keys. The easiest thing for me to think about is a universe of variables and values. Right? And the operations, so this is the universe. And the operations then are really just going to be, at least for the time being, just read and write. Right? So for example, there might be a client connecting with a data store. Let's just call it, instead of calling it R, if we're going to use the terminology, let's call it DS. Right, so the client might, for example, say, I would like to set X to 1. I've been using this kind of notation all along. Well, let's just make it formal. These are the operations you can do. You have variables and you have values. You can set the variables to certain values. And you can request to read a particular variable, in this case, Y. Actually, let's make it X, since we don't know what the value of Y is. And the data store can respond with the value of the variable you requested. Let's just do that. I think that's sufficiently general to model actual databases, key value stores, file systems, my memory on my computer, a distributed programming language interacting with a shared memory, whatever. So let's keep our model simple. There's variables that take on values. The values could be compound, they don't have to be integers, but I'm always going to make them be integers to make my life easy. Let's ask ourselves very, very abstractly, and I think we already began asking ourselves this during Lindsay's lecture. Given that we have name variables and these sort of write operations that just sort of make the variable take on a new value, we fundamentally have like time-varying operations that we have to model, right? So we have this situation in which if two clients set X to some value, after both of them have done their operations and somebody comes along and does read, what are they going to read? Well, one of these two. And which one they read is going to depend on what? Whoever came last, right? Because that's the semantics we expect from variables, registers, keys, right? The so-called last writer ones. Right? This means that obviously, if it were possible for two arrows to touch down in the same place, something that I've said we're going to pretend isn't possible on a single timeline, but obviously would be possible if there was a DS prime out here, right? It's going to give rise to a number of what we might call conflicts. Now, when Lindsay lectured last week, she invited you to sort of a more graduate level sort of discourse around what if there were a world in which we knew enough, we had not had this wide open API, we had in fact a restricted API, in which we said things like, oh, you don't have variables that can be assigned things, maybe you have sets into which you can union things or something like that. We're not going to make that restriction. We're going to try to be maximally general, which means that conflicts can arise. It's not going to be the case that every two operations somehow have a least upper bound that reconciles their effect on the distributed state, right? So what do I mean by conflicts? Well, in a universe in which there's variables and values, and the things you can do to them are read and write them, what are the sorts of things that could go wrong if multiple things happen concurrently? Yeah? Yeah, and when you say read the wrong thing, I think there's two versions of that, right? There's what you might call a read-write conflict. This is borrowing from the database terminology a little bit, right? In which write-read conflict. Thank you. Who said that? Thank you. Yeah, write-read conflict. In which, you know, for example, let's say I have a client. I have a data store, and I have another client. And if this client says x equals 1, but let's imagine that x's initial value is 0. And then this client comes along and says read x, and they get back x equals 1. These two transactions conflicted because had they happened in a different order, had this arrow touched down here, I would have read a different value. I wouldn't have gotten x equals 1, right? I would have gotten x equals 0. So we see that these two operations conflicted is just to say that the order in which they happened had an effect on the outcome, right? Because if the read had happened before the write, it would have been a different value. But there's another kind of conflict that can happen, right? Which is what you might call a read-write conflict. Now, in a read-write conflict, something like this happens. I read a value, I read x, I get back its initial value 0, as you would expect, and then you came along and wrote x equals 1, right? In this case, it's the same thing, isn't it? How is this different? Read-write, read the thing that you wrote, and I wouldn't have read it otherwise. The difference here is that you've gone ahead and clobbered something that I read that I might expect to stay the same. Now, finally, two writes can conflict, because I can have two writes x equals 1 and x equals 2, and obviously the order in which those two lines come down is going to affect the final state of x visible to any future data. Right? Given these three kinds of conflict, we can generalize conflict and say a conflict occurs in a storage system when what? When two operations do what?
Access the same variable.
Access the same variable. And I mean, and obviously replace variable with table or row or key or whatever the hell the granularity is in your model, but that's why I argue that variables are general enough to model everything we want to do.
Would it be two operations or two processes?
Say again?
Would it be operations or processes? Because if only one process is talking about the one variable, I guess their messages could touch down in opposite order.
You're right. I mean, they should be two operations originating in different processes, or at the very least in concurrent threads or something like this, right? Access the same variable, and there's one more.
The outcome.
Well, let me give you an example of something that's not a conflict. Read x, read x. I do not care what order those things touch down in, provided there wasn't a write in between them or something.
At least one of them is a write.
And one of them, at least one of them, is a write. That's what a conflict is. Now, does that always mean there's a conflict? No, because if the value stored in x was a set, and the operation was union, we would be writing to the same variable, but there would be no conflict. Right? Because it doesn't matter what order unions happen on. This is a conservative definition. If we can rule out these things happening, we can rule out conflict. Okay. Kind of slightly given away here, but. So these two are at the same time, and that's why it's conflict. Yeah. And then to illustrate, like, it doesn't appear to be a conflict. There doesn't appear to be a problem here. There's only one database. And I'm just saying, like, even when there's only one database, observe that the final outcome of operations of this flavor is going to depend on the order in which they happen. Now, if everybody buys me with that, then it shouldn't be that much of a stretch to say, now let's go back to that picture I like to draw, right, with the 4 lines. And say, now if I had D1 and D2 instead of just D, you can see how if client 1 issues a write and client 2 issues a write, I care very much about the order in which they touch down on the 2 lines, because if they're writes for the same variable, they are in conflict. And now that there's 2 Ds, there's an opportunity for the 2 different conflicting orders to happen. Right? So that you get in a situation like this is x equals 2. And at the end of the day, this replica thinks that x equals 2, and this one thinks that x equals 1. Okay, so the problem is that there's a class of operations for which the order in which they occur affects the final result. Which means that if those events happen on distinct machines, distinct replicated machines, what? What do we need to do if we need to make those machines at the end of the day agree? Well, we don't necessarily need consensus, but we need to establish a total order. We need to be able to say, event X happened and then event Y happened, so that we can decide how to arbitrate among these conflicts. If all the replicas agree, okay, look, x equals 1 and x equals 2 are in conflict. But if everybody agrees that x equals 2 happened last, we don't care about the conflict. We just pretend x equals 1 happened, nobody saw it, and then x equals 2 happened. That's fine, right? So the name of the game in replication, if we want it to be a term that I haven't introduced yet, I don't think, strongly consistent, we're spending a little bit of time on that. Trick is going to involve establishing a total order over the operation. Okay? And establishing a total order over operations is trivial when there's only one database. Why do I say that?
Whatever I received it, that's the order.
Exactly. So a great way to choose a total order is to choose it based on the order in which you receive the messages. And as I've already said, you can only receive the messages in one order. So if it's just one database, you're like, I don't care. Like, these things were racing, and like this guy won, and I don't care. And that's what happened. The total order is 1, 2.